This is an update of the kinetics of rigid bodies chapter. The summary is sort of on section 6A of Merriam and Craig and chapter 17 of Hibbeler. In essence, what I'm trying to do today is maybe talk a little bit more than I have in the past about mass moment of inertia of a body. Again, define the equations of motion for a symmetric rigid body and look at translation, rotation about a fixed axis, and general plane motion. This part of the course, one of the big things, of course, is that the body, whatever you're looking at, has a size and shape. That means an applied force can cause the body to both translate and rotate. We talk about the three different types of motion later, but it ends up that you have two governing equations, sum of forces equal mass times acceleration, and its correspondent moment equation, sum of moments equals Ig alpha. Now the tricky bit here is Ig, which is not a universal constant like mass. You've got translational components of acceleration and rotational components of acceleration to deal with. Moment of inertia is a measure of the resistance of the body to angular acceleration. So similar in terms of ideas to what mass is, but it depends on where that rotation is trying to occur. So for a moment of inertia about the z-axis here, where we have a rectangular body that has a radius or a direction r about the z-axis, or a distance r about the z-axis, it's I equals r squared dm over the entire mass. Mass is going to be defined as a small cubic element of del x or dx, dy, dz size with a density of rho. So there it is in the body. And I can sort of rewrite things and say, well, the integral of that could be rewritten as r squared rho dV. Now, rho has units of kilograms per cubic meter. And so it often is a constant value, especially in this course. I'm not going to deal very often with variable densities. But, you know, for example, if you want a variable density problem, make a peanut butter sandwich. And in there, you're going to have different elements of different densities to deal with. Typically, we're looking at, say, a steel pipe or something of that nature, which is going to be uniform in density as far as we're concerned. And again, most times in this course, actually, probably 99.999%, the density is constant. dm is equal to rho dV. And we have in the course a number of standard shapes. And these are sort of the three-dimensional equivalents. You have the cylinder, m2 is times m over 2 times r1 squared plus r2 squared. If r1 goes to 0, it's just a solid cylinder. You have a flat plate, m over 12 h squared plus w squared. You have a flat plate at one of the ends, m over 12 4h squared plus w squared. We'll talk about this in a few minutes. And a sphere, and I'll actually go through a derivation, of this case in the moment of inertia presentation. But for a shell, a spherical shell, you get 2mr squared over 3, and for a solid, 2mr squared over 5. We don't do much in terms of the derivation, but it's just a really quick derivation. Again, I about point A is equal to r squared dm, so that would depend on distance. And I can rewrite that as d plus x prime and y prime squared, the distance up. Now, y and y prime are the same. D and x prime are dependent on distance from g, and I get IA equals x prime squared plus y prime squared dm plus 2d x prime dm plus d squared dm. D squared is this constant distance between the center of mass and point A. IA equals Ig plus md squared. Now, it's important to understand Ig does not equal IA plus md squared. It is specific to the derivation that got this result. And so it's important that you understand how you get these numbers. And this last term, because it's about the center of mass, 2d x prime dm, it's going to have half the mass at negative x prime and half the mass at plus x prime, and this term will go to 0. So in terms of parallel axis theorem, the typical case most people deal with, and it's a struggle often when you deal with them for the first time, is say something like a rotational motion where you have a pinned rod with a center of mass g and a distance L over 2 away. The acceleration of g is a translational acceleration, and it has a rotational acceleration. I naught can then be written as ig alpha, or I naught alpha. It can be written as ig alpha plus mag L over 2. But ag equals L over 2 alpha, and so I naught alpha equals ig alpha plus m L over 2 squared alpha, which just happens when you pull everything apart, ig plus ml squared, ml over 2 quantity squared over times alpha. So this term right here that we're talking about is the one that we kind of expect to see, and that's the parallel axis theorem. The other thing you get is radius of gyration, and radius of gyration often again starts to be confusing because people say, well, you know, I've got this flywheel, it's a disk, but you're giving me a radius of gyration. The radius of gyration is always going to be ig equals mk squared. K is the radius that you're given. It's usually in units of meters or millimeters or something of that nature. So when you have this complex shape right here, which is a artistic representation of what I think is great art, that was also equal to this hoop, all of the mass spread a distance k from its center. But ig in this case is always going to be mk squared. And k, again, units of distance, ig over m square rooted, units of length. The other thing is composite bodies. You often have composite bodies when you're dealing with these problems. And when you have components like this, you often use tables. So the one thing that you really should know are these two objects. So this object right here, slender rod, and a disk, a thin disk. And those you kind of have to have in the back of your mind. It's not as important. If you look at the crib sheets that you were given and other things, you will find that information in there. But I strongly recommend that you at least know slender rod and a disk for your moments of inertia. So you have a slender rod of disk length L, disk of radius R. Center of mass of the rod is given at the center of the rod, and the disk is at the center of the disk. There's a pinpoint over here, and you want x of the system, m rod, xg rod, plus m disk, xg disk. Know how to do this. Again, this is something I'm finding in Piazza that a lot of people are sort of struggling with this idea. It's a mass-based average of the location of the center of mass with respect to the amount of mass of the object. So mass of the rod plus xg rod plus mass of the disk, xg disk, over a mass of the rod, mass of the disk. So if the disk is 90% of the body, it's going to be shoved towards the disk. If it's 10% of the body, it'll be shoved towards the center of mass of the rod. Y of the system, same thing. Y mass of the rod, yg rod, mass of the disk, yg disk, mass of the rod plus mass of the disk. So substituting in terms, using the parallel axis theorem, you end up with this expression right here about the pin. 1/12 mr squared, which is for a long slender rod, m rod L over 2 squared, parallel axis theorem, plus 1/2 mass of the disk times r squared, which is again for a thin disk, and mass of the disk r plus L, which is parallel axis theorem. Rod and disk. Be comfortable with both of these ideas. Radius of gyration, previous slide, and this one using composite bodies and describing them in terms of their component parts and using the right mass for each term. In terms of motion here, you always have the same sort of motion that you found in the previous chapter, as you have translational and rotational. Motion is parallel, rectilinear, or curvilinear. That is, again, straight line or curved path. Equations from the particle kinematics still hold. And sum of forces equals mass times acceleration g. Now the thing is that depending on the motion, if I have straight line motion, I'll use x, y, and moments about g equals 0. Some forces about the normal and tangential if I'm using curvilinear translation. So if it's a curved path, I'll use normal tangential, which is, again, it's not as exciting when you're doing particle kinematics or particle kinetics when you're looking at NT systems. But this time it starts to make more sense, and mg equals 0 again. In rectilinear translation, if you have a point A that's off, and which lies at a perpendicular distance d, so this is d over here, then what you'll end up with that the sum of moments about A equals sum of the kinematic motion or kinematics about A. So sum of moments about A is mag times d. So the resultant acceleration times the mass times the moment arm gives you the moment about A. So even though you have rectilinear translation, as long as you're off the center of mass, and you have all of these motions over here, even if you have rectilinear translation, as soon as you go off the center of mass, you have a moment. For curvilinear translation, we go from xy coordinates to nt coordinates. So you have mass times acceleration g in the normal direction, some force is tangential, mass times acceleration g in the tangential direction, some moments about g equals 0. Moment equations, again, if you shift off there, you're going to have to consider the perpendicular distance from the curved path from G to A. So here, for example, E in the normal direction and H in the tangential direction. So E times the MAG tangential and H times the MAG normal. Now here I'm keeping to a coordinate system consistency, and so tangential coordinates and normal components in this direction. Then we have rotational motion, so everything is pinned at point A, or O, excuse me, and you have the sum of moments, or you have rotation, and the point G has mass times acceleration normal and mass times acceleration tangential. So you add in all the forces that are acting there, and you add in the terms alpha, omega. If you substitute in all of your expressions, you have sum of forces normal, sum of forces tangential, moments about G, and you have moments about O, which is equal to I naught alpha. So that equals IG alpha plus MAT RG. Remember that previously when we talked about parallel axis theorem, it really is a way of translating moving that translational component of acceleration, and we end up with IG plus MRG squared alpha for that term, and it puts it around point O. That's good. And finally, you have the acceleration, or excuse me, the general plane velocity terms, sum of forces in x, y, and z, moments about g, x, y, moments, or mass times acceleration x, mass times acceleration y, moments about g, ig, alpha. And forces acting there, you have moments, and you have alpha, omega. So out of this, what do you have? You really have the important concept out of this chapter is radius to gyration and parallel axis theorem, but also how to apply these ideas to the three types of motion: translation, rotation, and general plane motion. Identify what they are, identify them through drawing these pictures, looking at what they are, and then get comfortable with the idea that sometimes, again, something that's happening instantaneously can be described very well with these three laws. Thank you.